what we're going to be talking about is we're going to be talking about chemistry of benzene. Now, when you look at the structure of benzene for the first time, the first thing that you should think of is, you know, what's so special about benzene? It just looks like a ring, okay, big deal. That doesn't change anything. It's got double bonds. We already talked about the chemistry of alkenes. How different can it be? Turns out very different, and not at all like what you expect for an alkene. And we're going to find out the ways in which it differs, but more importantly, why. So first of all, we have to do the necessary, the needful, and that is we have to talk a little bit about nomenclature, unfortunately. So the nomenclature, mercifully, is not too bad. I mean, chlorobenzene. Yeah, it makes sense. Nitrobenzene, you know, bromine, bromobenzene. However, there are many common names that are not systematic, but are simpler benzene derivatives. And these are not things I'm going to ask you on an exam or a quiz or whatever. I'm not going to ask, obviously I won't. But you need to know what these things are, or you're going to be mystified when you read the book and whatnot. And so phenol, that's hydroxybenzene. Toluene, catechol, hydroquinone, anisole, styrene. Styrene you've seen before. Anisole, anise, gee, what does it have? Yeah, this has a very nice odor. It smells sort of like, I don't know, you guys are too young to drink, but maybe not all these. Anisette, okay, French aperitif has that's what that smells like. Or if you're from my parts, ouzo also has that in it. So this smells pretty good. This stuff smells horrible. Xylenes are dimethylbenzene. So there's an ortho, a meta, and a para-xylene. And this introduces us to this ortho, meta, para nomenclature. Obviously, if you have two substituents on that six-membered ring, there are three ways that they can be arranged. They can either be next to each other, in which case it's a 1-2 relationship, that's ortho. It can be 1-3, that's meta, para, and 1-4. Obviously, if I move it over 1-1, then it becomes 1-3 again, and it's meta. So these are the three isomers of any disubstituted benzene. Okay. So far not that bad. I mean, there are unfortunately an awful lot of trivial or common names, and you know, it's a good idea to try to remember some of the more useful ones. Phenol, for example. I mean, you know, you should know phenol, especially those of you who are biologists, because we use phenol for what? For denaturing proteins, right? So anyway, if you have three substituents, you know, you alphabetize, so 1-bromo, 2,3-dichlorobenzene. You can look up the rules. The rules are all pretty much the same things, the same ones that we talked about before, given the smallest numbers and so on. A couple of things you need to that are confusing, and that is if I just have this substituent, right? This piece here, that's a phenyl. If I put a CH2 in between, that's benzo. And boy, is that confusing because, you know, benzyl, benzene, and you think, well, gosh, this should be benzyl. No, this is phenyl, this is benzyl, okay? So it's not logical. I didn't make up the rules, but we do have to remember them. So phenyl is just the aromatic ring. Benzyl has an additional CH2. So if I have this compound here, this would be diphenyl ether. If I had this compound, oops, this would be dibenzyl ether because I have the CH2 groups here. So these groups are benzyls. Phenyl is that piece there. So this piece is phenyl. Once I put the CH2, benzyl. Okay, so phenyl, benzyl, don't get them mixed up. I know it's tough. So benzyl bromide, for example, we're going to see this as an electrophile. Okay, so now a little bit about physical properties. Nothing too unusual here, nothing strange. The physical properties are just what you'd expect pretty much for hydrocarbon, right? So boiling point for benzene, not that much different from cyclohexane. Melting point the same. But what happens if I put a methyl group? Put a methyl group on the benzene. Boiling point goes up. Okay, it goes up a little bit. You expect that because molecular weight's higher. But look what happens to the melting point. Melting point goes way, way down. Look at the difference of those two. And so the question is, why? And what is it about that methyl group that makes the melting point of benzene change so much? Benzene by itself, you know, it melts above 0 degrees. You put one methyl group on there, and boy, you get, you know, 100-degree difference in melting point. Why? Yeah, symmetry. That's exactly right. I mean, these are two highly symmetrical, so more ways that they can fit together in a crystal. Just that one methyl group destroys that symmetry enough. I mean, it still has symmetry, but it destroys that symmetry enough to make that big difference. That's kind of I mean, that always surprises me when I think about that. By the way, you see that not just for methyl, you see it for all substituents. So, for example, the para-isomers are always going to have higher melting points than the meta-isomers, or the ortho ones. And so here's a good example. The para-isomer melts at 55 degrees just about. This one is below 0. And so the reason, again, is that when you have the para-isomers, they stack better in a crystal than the ortho or the meta ones. And so this is kind of a general trend, which means that any kind of para-disubstituted benzene becomes a little bit easier to purify by recrystallization. Okay, so talking now about more physical properties, let's talk about spectroscopy. So we're talking about benzene. Forget about toluene, nitrobenzene, phenol, just the benzene ring. What do you have in there? Well, you have double bonds, right? And so you expect to see an absorption in the double bond region, and you do. These frequencies are a little bit lower than for alkenes, right? You know, alkenes are a little bit higher than that, but these are a little bit lower. And that's because the bond order in benzene is 1.5. It's not 2. What does that mean? Why should it be 1.5 instead of 2? I mean, if I look at benzene, you know, I see a double bond, a single bond, a double bond, a single bond. However, I can write a resonance structure for benzene, and what was a single bond here is a double bond there. What was a double bond here is a single bond here, and so on. And so, as a result, because those two resonance structures have identical weights, then the bond order is going to be 2 plus 1 divided by 2, which turns out to be 1.5, right? Because this bond order is 2, that's 1. Add them up, that's 3. Divide by 2 resonance structures, that's 1.5. So bond order is 1.5. Okay, so, and that, by the way, is going to be reflected in the bond length, too. The bond length is, the bond distances, by the way, in benzene, they're all the same. We don't have short bond, long bond, short bond, long bond. They're all the same size, and each bond has bond order of roughly 1.5. Okay, so that's reflected in the IR as it should be. So in other words, if I saw it, if the IR gave me a different number, if it looked like a pure double bond, then I'd scratch my head and I'd say, I wonder if I have an alternating bond length, short, long, but you don't see that. Proton NMR is absolutely characteristic. And so for benzene, they come at 7.4. Now that is way de-shielded, right? So for an alkane, which is an alkane of cyclohexane, and then you'd expect the peaks to be at, well, 1.2, 1.3, somewhere like around there. And now we're all the way to the left-hand part of the spectrum, and the benzene peaks absorb at a little past 7. And if I put electron withdrawing groups on that benzene ring, guess what happens? It moves even further downfield, further de-shielded. And so now the question is, how come? But we've seen this kind of thing before. Remember, and I told you it was going to come back. That was the magnetic anisotropy that we saw for alkenes. Well, same kind of thing here. Nothing new. This is just the same kind of situation that you have. Remember what the situation was for an alkene. that you had an induced magnetic field by the circulation of the pi electrons in the double bond. So pi electrons felt the effect of the external magnetic field, and then there's an induced field that opposed the applied field in one part, but augmented it where the protons were. Same thing here. And so I tried to show that again with this little cartoon. So I have the benzene ring perpendicular more or less to the plane of the paper. The applied magnetic field from the magnet is B naught coming up this way. That induces circulation of these of the pi electrons, which are above and below the plane of the ring, and that induces a secondary field in green, an induced magnetic field, which reinforces B naught right there and right there. And so where the protons are, what do they feel? What do they feel? They experience B naught plus B1. Up here, on the other hand, they will experience B naught minus B1. So if I could somehow put a proton right there, your prediction would be that that proton would be shielded. And there's a problem in the text that kind of asks that question. And so, of course, you're not going to put a proton all by itself. You have to have an alkyl chain. But the point is that the aromatic protons are strongly deshielded because of this magnetic anisotropy. Now, remember that the benzene rings are not always going to be oriented perpendicular to B1, to B naught, pardon me, but that we're averaging all the orientations. It's just that this particular orientation is very important, has a big effect, and so that's why all the protons are way downfield. So the induced magnetic, this is just what I said, the induced magnetic field opposes above and below the plane, but reinforces it in the periphery. And the periphery of the ring is where the protons are, so the protons are strongly deshielded. That's why that's 7.4. So this is our second example of magnetic anisotropy. Now it turns out there was a third example of magnetic anisotropy that I didn't talk about in Chem 272 because we haven't covered NMR. But if you're curious, go back to the chapter on alkynes. And there's going to be a little, I think that's chapter 14, and there'll be a little section in there, 14 or 15, there'll be a little section on NMR of triple bonds, and there's a little discussion of magnetic anisotropy there as well. Okay, now coupling constants in benzene, just what you'd expect. The 3-bond coupling is strong, the 4-bond coupling is weaker, the 5-bond coupling is really very weak. The problem is this, that when you have let's say a disubstituted benzene, or even a monosubstituted one, all of these couplings are taking place simultaneously, right? And so the splitting pattern for aromatic peaks is very often not first order. And so very often you just see a complicated multiplet. You can't really distinguish the individual coupling constants. Sometimes you can, but not always. And so the ones where you can always distinguish coupling constants are the para-disubstituted case. And so para-disubstituted, when I say para-disubstituted, by the way, I'm talking now about two different substituents, X and Y. What's X, what's Y? I don't know. But maybe a methyl and a nitro, or a chlorine and a methyl, or something like that. And so as long as X and Y are different, then you see a very characteristic pattern, which your book shows. And this is, by the way, from 5th edition. And so what it's going to look like, that pattern, it's going to look like this. So it looks sort of like a quartet. And but these two protons, the deshielded ones, are going to be the two that are next to the more, let's say Y is more electron be these two, and then the other of these two. So that pattern is very easy to distinguish in a proton NMR. So if you see what looks like a quartet in the aromatic region for an NMR, then you know that that's going to be a para-disubstituted benzene. Okay, so chemical shifts, again, please don't memorize these. You can find these in tables, but the benzylic methyl is deshielded, right? You know, methyl groups don't come at 2.2, they come around 1. So why is this one deshielded? Well, you know why, because it's in the periphery of the ring, and the magnetic field that this methyl group experiences is the applied magnetic field plus the induced magnetic field, so it's deshielded. So anything that is bonded to the benzene ring is going to experience the same field as the protons, maybe a little bit less because the protons are a little further out, but nonetheless deshielded, right? And so that's what that number is telling you. C13, again, no surprises. The aromatics all come around, you know, between 120 and 130. And the nice thing is that remember what we said about C13? We said that it does a really good job of spreading the peaks apart. So a proton, if you have a simple hydrocarbon, then the spectra are rarely, if ever, first order. But for C13, because you're looking at a much wider frequency range, you're looking at 0 to 200 ppm, you get much better peak dispersion. And you can see that here. In other words, each one of these carbons appears at a slightly different chemical shift. And you can see what's the difference between 125.4 and 0.5. Hey, that's plenty enough to see by NMR. You'll distinguish these two. That's a tenth of a ppm, and a tenth of a ppm is no sweat to pull apart. So for this particular aromatic, how many peaks total are we going to see because of symmetry? Well, these two are going to be different. These two are the same, these two are the same, right? So it will be, if I count carbon atoms, this has 8 carbon atoms, but it's going to be 2 minus 8, 6 different peaks. 1, 2, 3, 4, 5, 6. 6 different peaks for this one. And notice, of course, that the methyl here is about the same place as any other metal should be, because it's far enough from the ring. Okay. So carbon, oh, the other thing you should know, yeah, I pointed this out, that this carbon, C13 NMR peak, is going to be a small peak. It's going to be a little tiny one compared to the others, and that's because of what I said. Carbons that are bonded only to other carbons, don't have any hydrogens attached, those are small peaks. And so figuring out in the C13 spectrum which peak is responsible for that carbon atom, very easy, that's a small one. And you'll always be able to make that distinction. Okay, UV we don't talk a lot about, right? I mean, UV is sort of the orphan child of your spectroscopy these days, because you don't get, I mean, the information you get from the UV, typically you can get better information from C13 proton or even IR. And so we don't use UV a lot. That's not to say that there aren't instances when it gives you unique information, but for you know, we're not going to see this again. So you have 2 lambda maxes for benzene. And anytime you have a substitution, substituent that has a lone pair, that has a pi bond, that will both increase the intensity and move the, it'll move to a longer wavelength. Now this is general, not just for benzene rings. I think we mentioned this when we talked about UV. So in other words, if I have 2 double bonds in conjugation, that's going to have a UV absorption. If I then compare the UV absorption of that compound with one that's like this, it's got 3, both the intensity and also the wavelength are going to increase. And so the same sort of situation happens when you have, say, benzene, and then something where I add another pi bond here, when I have styrene. So for styrene, the same thing's going to happen. You're going to have an increase in intensity and a shift to longer wavelength. And it turns out to be related to the size or the length of the pi system. And I won't go through that for you, but if you take a quantum chemistry course, this is one of the first things, first problems that they ask you to solve. And so it manifests itself in benzene UV by, as I said, shifting the longer wavelength and seeing an increase in density. So anytime you have a non-bonding electron pair or a pi molecular orbital that can overlap the benzene ring, expect that effect. Okay, so that kind of wraps it up for physical properties, spectroscopy, nomenclature, and so on. Nothing particularly new here. Not even magnetic anisotropy, something we'd seen before. But now for something new. This is the kind of the heart of this chapter, and that's the reactivity of benzene rings. And benzene rings, and by the way, what we talk about with respect to benzene is going to be true in general terms for other aromatics. So benzene is not the only aromatic ring that we have. We have others. For example, if I put two benzene rings together, like so, then this is naphthalene. And naphthalene will react pretty much the same as benzene, with a few little twists. And so when we talk about the chemistry of benzene rings, be aware that it's not just benzene. It's this whole class of compounds that reacts more or less the same way. So the characteristic reaction of these systems is electrophilic aromatic substitution. And so we're going to spend a fair amount of time talking about this. Now, the thing to recognize is that this is a new reaction for us. If I take benzene, and look, I've emphasized the hydrogen here. Okay, so I'm looking at this carbon atom and it's bonded to a hydrogen. And I allow that to react with an electrophile. I don't care what the electrophile is. In fact, it doesn't matter. Every electrophile is going to react the same way. What I get is I get a very strange reaction where the hydrogen is gone, it's over here, and instead of a CH bond, I have a C bond to the electrophile. Now, this is not an addition reaction. I'm not adding EY to the benzene. An addition reaction would be benzene, and then I'd have a bond, a carbon X, and a carbon Y bond, and all the hydrogens in benzene would still be there. But no, the hydrogen's gone, so I've substituted this hydrogen for the electrophile. So this is what we mean by substitution. Hydrogen substituted by electrophile. So I've replaced the hydrogen by an electrophile. Okay, so this is not the same kind of reactivity that we've seen for alkenes. Not at all. Why? Well, because remember, what happens if I take an alkene and I treat it with an electrophile? If I take a normal alkene, let's just say cyclohexene, right? And I treat this with an electrophile, E+, a strong electrophile, then I'll get one of two things. I'll either get a three-membered ring of bromonium ion, remember, or depending on what kind of electrophile I use, I'll form a cation like this, or whatever. And then if the counter ion is X minus, then what will happen is I'll get EX, where I've done the addition to the alkenes. The alkenes wiped out, the protons, so proton here, proton there, they're still there. That's the reactivity that I get for alkenes. That's not what happens with benzene. Benzene, you get something completely different. Okay, so let's take a look at some examples. Now, what was the first example of an electrophile that we used when we talked about alkenes? Which one did we look at first? Bromine, yeah, okay, so bromination. So, we do halogenation reaction. So, if I just take benzene by itself with bromine by itself, nothing happens, okay? You don't get any reaction. Or if you get some reaction, it's really, really, really slow. And that's very different, right? Because you look at benzene, you say, it's got three double bonds, geez, they've got to react. No, they don't. And the only time they react is in the presence of a catalyst. The catalyst that's used is typically iron bromide, ferric bromide. This is iron +3. Now it turns out for the catalyst, you can actually add iron powder. A little bit of iron powder works. Why is that? Because bromine acts as an oxidant, oxidizes iron metal to ferric bromide. But ferric bromide is the active catalyst. This would be a pre-catalyst. So you get the catalyst here. So you need a catalyst, and then you get aromatic substitution. You substituted that hydrogen with a bromine, and you formed a molecule of HBr in the process. On the other hand, if I tried to do the same reaction with cyclohexene, remember what happens. I get a bromonium ion, bromide attacks the bromonium ion, end up with a vicinal trans-dibromide. And that's different. That's not the same at all. Now, the same reaction that we just showed for bromine, it takes place with chlorine too. So I can use chlorine here. I probably want to use ferric chloride so I don't get mixture of bromine and chlorine in the product. And I get an aromatic substitution where the hydrogen is substituted by a chlorine. It's not an addition reaction, it's a substitution reaction. This reaction does not take place with iodine. Okay? There are ways to get aromatic iodides, but not this way. And we'll learn about that sometime, I think 4 chapters from now. Okay, so right now we're confronted with kind of a weird situation because benzene, it's not reacting at all the way it should, and it's reacting in a very different way, and we need to understand what the catalyst is doing. Okay, so I think I mentioned this at one point. If you have a metal in a high oxidation state, like iron 3, iron 2, iron 0 is the lowest oxidation state. You have ferrous ion, that's iron 2, then ferric, iron 3 is the highest oxidation state. You have a metal in high oxidation state that's bonded to electron withdrawing groups. Those are always going to be what? Going to be Lewis acids. So ferric bromide, ferric chloride, those are Lewis acids, good Lewis acids. And so here's what happens. The role of the Lewis acid here is to convert Br2 into an even more reactive source of Br+. Okay, so Br2 is a source of Br+, sure. We just saw it react as a Br+ with cyclohexene. But it's not as reactive as it has to be to react with benzene. So we need something that's more reactive than bromine if we're going to get a reaction with benzene. So what does ferric bromide do? Well, I've shown the Lewis structure here, but really this is what's happening. What do Lewis acids do? What's the definition of a Lewis acid? Electron pair acceptor, right? Okay. So this electron pair moves over to the iron. That's kind of what I've shown with this line. Now, once you do that, this bromine-bromine bond gets polarized. And so this bromine now has a delta plus. And so this becomes now a very good electrophile. So that's a much better electrophile. Now, there are several ways to look at it. You can say that, well, this is a much weaker base than Br minus, therefore a better leaving group, and therefore this is activated. That's saying exactly the same thing. Okay? So this bromine is polarized because of this interaction. And so it reacts, it's sufficiently reactive to react even with a benzene ring. And so you end up with this intermediate. Now, this intermediate is resonance stabilized for sure, right? I can write 3 resonance structures for that. I can write the positive charge either here or there or there. So the positive charge is either at these 2 carbons or that one. Okay? And please, if you've forgotten how to write resonance structures, now is the time to remind yourselves, because we're going to be doing a lot of it in this chapter and from here on out. Okay, so this chapter is going to be a chapter where we talk about mechanism a lot, where we talk about resonance structures a lot, and so on. So this is a little bit of a review of some stuff that we heard in 272. Okay, so let's recap and see what happened here. So we start out with benzene, we have bromine, and we need this catalyst, right? And so the catalyst activates the electrophile. Now we have a much better Br+, much more reactive than this one. It reacts with the aromatic ring to generate this intermediate cation. The cation is resonance stabilized. However, you have lost aromatic stabilization in the first step. So the aromatic stabilization that you have for the benzene ring is nowhere to be seen. It's gone. So that's why you need such a reactive source of Br+, because it's going to cost you some energy, roughly 35, 36 kcals per mole, to lose that, less than that because of the resonance stabilization of this, but substantial amount of energy to disrupt the aromaticity of that ring. And that's why benzene doesn't react. Remember we talked about aromatic stabilization. So, so you lose that aromatic stabilization in this process. And that explains the reluctance of benzene to react with weak electrophiles. Okay, so fine. So now we're here, but we're still not at bromobenzene. So let's take a look. What needs to happen to this cation to convert it to bromobenzene? Yeah, you need to lose a proton, not a hydrogen atom, but an H+, right? So the H+ you lose is this one here. That has to leave as an H+. Once that leaves it as an H+, then you got bromobenzene. So what's the strongest base you have around here? Well, it's probably Br-. And so Br- can pull off that proton. Now you have HBr. You still have ferrochromite, so ferrochromite is a true catalyst. Ferrochromite is now available to do it all over again. And you have bromobenzene. Now what never ever happens is you don't get this bromide coming in with this electron pair and forming the dibromide. Why do you never get that addition? Well, because this process is faster. Why is the top process faster? I mean, the bottom process is exactly what happens with cyclohexane, or cyclohexene, pardon me. But doesn't happen here. Here you get this. Why is this faster? When a reaction is faster, what are we saying? There's another way to say the same thing. Yeah, lower activation energy, right. And the reason the activation energy is lower is the same reason we keep saying. It's the Hammond postulate, because now you're going to an aromatic product, and so that aromatic stabilization is felt by the transition state. And so that's why this always outcompetes that. So now, actually, I just thought about this. There's another question you should ask. What is it? So we showed it's a little bit tricky, but here, let me, okay, so this is the reaction we showed, right? It goes from here to there, it goes to there. You should question this. Say, why does it stop after one bromine? Why doesn't it add a second bromine? I mean, I still have catalyst. There's still bromine present. Why don't I get a dibromide, tribromide, tetrabromide, until I've completely brominated that ring? Why does that not happen, you suppose? Well, you don't know yet, but we'll talk about that. So it is an important issue, right? I mean, because the same mechanism that I just wrote for benzene giving you bromobenzene, I can write exactly the same mechanism for bromobenzene going to dibromobenzene. And I can write exactly the same mechanism for di going to tri and so on. But it doesn't. It stops after one. And you can force it to go to a second time, but it takes much more forcing conditions. Why is that? Well, you can probably puzzle it out. If you think about the mechanism, and you think about what bromine's properties are, withdrawing electrons and so on, then probably you can figure it out. But we'll spell it out for you later. Okay, so this was our first example of an aromatic electrophilic substitution. It's not an addition, it's a substitution reaction. It goes through this charged intermediate that is resonance stabilized. Now, doesn't matter which electrophile you use, it's always going to be the same mechanism. So you're going to get sick and tired of seeing this mechanism because you do the same one each time. I'm going to go through it anyway because you're going to need to know it, and I don't want you saying, oh, but you only showed this one. Okay, so now we're going to do a nitration reaction. And nitrations are important because the nitro group can be converted to an amine and so on. Okay, so this actually is a little different for the following reason. Nitric acid, I've shown it this way, doesn't react with benzene by itself. And you need a catalyst. And the catalyst used here is sulfuric acid. You think, well, nitric acid, how does that work? It turns out sulfuric acid is a substantially stronger acid than nitric acid. And, nitric acid is already a strong acid. It just turns out that sulfuric acid is stronger yet. What this is doing is, it is protonating the nitric acid. Now that makes no sense, does it? Because you're getting an acid-base reaction with nitric acid acting as the base. So, you've never seen nitric acid acting as a base before. It's always been an acid, hasn't it? But in the presence of a much stronger acid, like sulfuric acid, guess what? It acts like a base. And that turns out to be key to the mechanism. So here's what happens. The first step is an acid-base reaction. Bronsted acid, Bronsted base. So, sulfuric acid donates a proton to that hydroxy. This is reversible. You get bisulfate as the conjugate base of sulfuric acid, and you get this protonated form of nitric acid. Okay, so this is the conjugate acid of nitric acid. This now, through the process that I've just shown, can spit out a molecule of water right there, and it gives you NO2+. NO2+ is a species we've not seen before. It's nitronium ion, and that NO2+, that is the active electrophile. So NO2+ acts in the same role as Br+ before to react with the aromatic ring. So the role of the sulfuric acid is to generate nitronium ion. Now once you have nitronium ion, then it just follows the same paradigm that you saw before. You get the electron pair forming a bond that gives you this cation. This cation has resonance structures. Loss of a proton gives you nitrobenzene, catalyst regenerated, and on and on and on. And so it looks exactly like what we saw before, no different, except the electrophile is NO2+ and not a Br+. Nothing new. So the only new thing is this proton transfer that generates the protonated form of nitric acid that then gives you nitronium ion, which is the active electrophile. Okay, so that's nitration. That gives you nitrobenzene. You can do, and please recognize that the mechanism was exactly the same, right? You get the electron pair from the benzene, forms a bond to the electrophile, gives you this charged intermediate. I draw each and every one of the resonance structures. Loss of a proton gives me the nitro. Why do I lose a proton? Well, because that regenerates the aromaticity, and that's always going to be the dominant pathway. Okay, so moving down the list of electrophiles, sulfonation. So I can do the same kind of thing that I did with NO2+. I can do it with sulfur. And in fact, here it's sulfur trioxide. So you can buy something that's called fuming sulfuric acid, stuff that you only use in a good fume hood. It's SO3 dissolved in sulfuric acid. Now you can think of SO3 as being the dehydrated form of sulfuric acid, right? So if I take sulfuric acid and I remove water from it, what am I left with? I'm left with SO3, right? And so sulfuric acid, you can think of this as being the anhydride of sulfuric acid. It is. And so this allows you to form benzene sulfonic acid, which is this stuff here. Okay. How does it work? Well, you know how it works. So you need a strong electrophile. Now this is a strong electrophile, but it can be made stronger by proton transfer to the sulfuric acid. And so sulfuric acid can protonate sulfur trioxide. So either sulfur trioxide or protonated sulfur trioxide gives rise to this intermediate. Here I've not shown each and every resonance structure because you guys by now should know how to do that. And then loss of a proton gives rise to the conjugate base, and you get this as your product because this is a weaker acid than sulfuric acid. So the sulfuric acid transfers a proton here. So that tells you that you need a stoichiometric amount of sulfuric acid here, right? It's not going to work with substoichiometric. Speaking of anhydrides of acids, if you look outside today and actually all week, what do you see? Vog, right. Okay, so Vog is SO2. What happens to SO2 when you add water? Okay, you get this stuff. H2SO3, not SO4, SO3. This is what irritates your eyes, okay? Now, if you take a piece of pH paper and you wet it and you waft it around for a while, my guess is that it will turn red. You can try that, by the way, and I've done this. If it's foggy weather and it rains a little bit, you just take a few of those raindrops and put them on pH paper. Boy, the pH is really low, and so you can actually tell that you've got some pollution. Okay, so let's recap. What did we talk about? We talked about electrophilic aromatic substitution, halogens. To get bromination, you've got to use bromine, but you also need to use what? You need to use a catalyst, ferric bromide. Chlorination, Cl2, and a catalyst. Iodine, we'll talk about later on. Nitration, that's kind of weird. Nitric acid by itself won't work. So you need to protonate the nitric acid with an even stronger acid. That's sulfuric acid. Sulfuric acid, nitric acid allows you to do nitration. Fuming sulfuric acid, which is sulfur trioxide dissolved into sulfuric acid, allows you to do the sulfonation. And this is a useful reaction. It gives you benzene sulfonic acid. Now, this reaction actually can be reversed. So you go from this all the way back to benzene by heating it with water. There are a few of these electrophilic aromatic substitutions that can be run in reverse. Bromination isn't one of them. And so we can talk about that at some future date. You should be able to figure out, just from this mechanism, what's going on. So, oh, this is one other thing, very important. I've shown all these mechanisms. I don't want you guys just looking at them or copying them down and saying, yeah, I understand that, I understand that. No, you don't. What you need to do is you need to write them out. So after you read them, get a piece of blank paper, put your notes in the book away, and reproduce them. Do it at least once or twice to make sure they make sense. I can guarantee you, if you don't do that, you're going to screw this up. So, and it won't take you that long to do it. So you've got to do that. Just looking at the mechanism, unless you're really good at this, it's not going to stick in your head. Okay, you need that extra reinforcement. Okay, so let's talk about now a little bit different kind of electrophilic aromatic substitution. The mechanism is going to be for all of these. It's going to be pretty much the same. So the first mechanism that you need to practice on your own, bromination, the very first one. Once you know how to do the bromination, the others are all pretty much the same thing. So is the Friedel-Crafts alkylation with a little twist. Okay, so what did we say way back when about organic reactions that form carbon-carbon bonds? What did we say? Yeah, pay attention to them because they're important, right? Because you don't have all that many. Well, here's one of them. So, so I think benzene, I think methyl chloride. Once again, I need aluminum trichloride as a catalyst, and I get toluene. So that's kind of nice. That allows me to form a carbon-carbon bond. Now, what the heck is going on? Well, okay, so you remember this, right? Remember that ferric bromide, acting as a Lewis acid, polarizes the bromine-bromine bond, and it makes this bromine a much better electrophile. Well, the same kind of thing can happen with methyl, where aluminum trichloride, acting as an electron pair acceptor, accepts one of the non-bonding electron pairs from this chlorine, and polarizes this carbon-chlorine bond, and activates this methyl group towards nucleophilic attack by putting a delta plus on that methyl. Now, the one thing you don't get out of the Friedel-Crafts reaction, or out of any reaction, is you don't get a methyl cation. Okay? So this looks, and if you just look at that, you think, oh, I know how that happens. I just have a methyl cation. Benzene attacks the methyl cation, yada, yada, yada. No. No methyl cations. Why no methyl cations? No methyl cations because methyl cations are very unstable, even more unstable in primary. Remember, we don't see primary. Secondary and tertiary, yes. Methyl and primary, no. Not stable. And you don't need a methyl cation. All you need is to activate that carbon-chlorine bond by sucking electrons out of the chlorine. Now that this has a delta plus, it's activated, and the aromatic ring can react with that in the same way that we saw for every other electrophilic aromatic substitution reaction, which means what? It means that I have the benzene ring, like so. I have the methyl, the chlorine, the aluminum trichloride. This has a delta plus now on it. I won't show the other charges. And I end up with this kind of reaction to give me aluminum tetrachloride minus. Here I'm going to get the, what am I going to get? I'm going to get a methyl group with a plus charge there and so on. And this has resonance structures, which I'm not going to bother to show for you because you can do it yourself. And then chloride comes in, pulls off that proton, and I end up with toluene. And so chloride from here comes in, pulls off that proton. This electron pair now forms the pi bond, and I end up forming toluene. Okay, so the mechanism is no different from any of the others. Start out with benzene, form a charged intermediate, lose a proton. How simple can it get? So, okay, so this is the Friedel-Crafts alkylation reaction. Now, it works, but it doesn't always work. So let's take a look at one that does work. Okay, so here I've taken 2-chlorobenzene, or 2-chlorobutane, and I want to do a Friedel-Crafts alkylation. So what do I do? Well, I take the benzene, I take the alkyl chloride, I take aluminum trichloride, I heat them up, and I end up polarizing carbon-chlorine bond. I end up with something that looks sort of like a secondary cation. The secondary cation that would be here reacts with the benzene, and I end up with the branched group on benzene. Good yield, right? And so then you think, well, geez, I could do the same thing with not 2-chlorobutane, but I should be able to do the same thing with 1-chlorobutane. And if I do exactly the same reaction, look what happens. I get a little bit of the N-butyl, but I get a lot of the secondary butyl. Now, what does that tell you? It tells you something that you've seen many, many times before. What happened? Now, okay, so what does it tell you? Yeah, when you see skeletal rearrangements, that tells you always that you had a carbocation. Okay, so we got a carbocation rearrangement here somehow. Is that surprising? Well, maybe not, right? Because when you look at the Friedel-Crafts, I said, well, you know, you never get a methyl cation. Sure, that's with methyl. But if I have secondary or primary, I can get rearrangement chemistry, perhaps, that gives me the carbocation. So that's the limitation of the Friedel-Crafts alkylation. You're not going to be able to get straight chain alkyls. The only straight chain, and I use the term loosely, alkyls that are going to work are methyl and ethyl, right? Because anything else can rearrange. Methyl cannot, neither can ethyl. But anything else, straight chain, is going to rearrange, and you're going to get rearrangement products. Now, tertiary works fine because it's already a stable cation. You don't need to worry about it rearranging. But anything else will rearrange. Well, is that true? No, I can give you examples where you're not going to get a rearrangement for other reasons. So, rearrangements are the hallmark of cations. And we've run out of time, so we're going to pick up on Monday. Oh, and for those of you who walked in a little bit late,